Rio Weil is going to talk about simulation algorithms for measurement-based quantum computing experiments.
Thank you for the introduction, and thank you everyone for sticking it out so far today, especially considering I am the last obstacle between you and a wonderful conference dinner. Today I'll be discussing some of the results and work I did for my honors thesis last year in collaboration with Robert, Arnav, Dimitro, and Amrit, some of which are here in the room with us. And to give a brief outline of the talk here, I'll start with some motivating questions in the field of quantum computation in general. Then I'll give a very brief review of measurement-based quantum computation before moving to discussion of one-dimensional resource states from MBQC. From there, we will depart the realm of theory and go into some experimental details before I discuss some of the algorithms as I alluded to in the title. Finally, I'll share some results and then kind of the second stage of the experiment where we moved into a so-called more quantum mechanical experiment to which I'll discuss whatever that means later. And finally, we will discuss a future outlook and directions. So to begin, although the existence of quantum algorithms that are conjectured to outperform known classical counterparts are known, such as Shor's factoring algorithm, kind of the fundamental element that makes quantum computers better over their classical counterparts still remains a mystery. There are many elements that appear to be necessary, such as quantum entanglement, but these themselves are not sufficient elements. Further, despite many of these kind of exciting algorithms being known theoretically, given the devices we have today, they're still quite noisy and small scale. Shor's algorithm is fantastic, but maybe not so much when all you can do is factor 15. So our talk is going to sit at kind of the intersection of both of these questions. For this first question of, what is the source of quantum computational advantage? I'll introduce the formalism of measurement-based quantum computing, which turns out to be a natural paradigm to discuss this question. And for the second question, we're going to be displaying results in measurement-based quantum computing on currently available quantum devices, hopefully giving us another use case, something interesting we can do with them. And here is our one-slide review of measurement-based quantum computation. On the left, we have our kind of standard circuit model of quantum computation. One starts with a initially unentangled product state. Then there's some computation-specific sequence of unitary gates, which evolves the state. And at the very end, there is a readout procedure where all qubits are measured on a computational basis. Here, the power source or complexity of the computation is really coming from this computation-specific sequence of gates we choose. On the right, we have the measurement-based model of quantum computation. And this particular graphic here is simulating the circuit-based model on the left. And what's interesting here is instead of starting with essentially a boring product state, you begin your computation with a special entangled resource state. Then the computation proceeds just via some sequence of adaptive single qubit measurements on this resource state. Essentially, the resource state acts as a universal canvas on which you can etch out any computation you like just by single qubit measurement. And this is helpful for this discussion of, where does quantum advantage come from? Because the question of, well, what makes a quantum computer special can then be recasted to, well, what makes certain initial resource states special and how can we classify them and their power? And for the remainder of the talk, I'll be talking about measurement-based quantum computational resource states in one dimension, which are able to simulate one logical qubit, as you can see from the equivalence here, where there is a lot of interesting current results and theory to explore, even if not universal. So I've been throwing around the term of computational power a lot. It'll be useful to have some operational definition for what this means. And I'm going to mean it as the ability for a state to harness arbitrary unitary operations. And in our case, because we're looking at one-dimensional states which can simulate a single logical qubit, this corresponds to the ability to perform rotations. And now we kind of have the two quote-unquote extremes of one-dimensional states that one can start with. On the left, you have the cluster state. So this is a universal resource, the ground state of this Hamiltonian here. And this, it can essentially harness any rotation you want by a adaptive set of measurements and without errors. On the right, we have a completely unentangled product state, and this will completely fail if you try to do measurement-based quantum computing in it. You can think that if I try to measure different parts of this state, it's just not, there's going to be no communication between different parts due to the lack of entanglement. An interesting question then becomes, well, what if we look at states in between these two? If we take these two parent Hamiltonians of the cluster and product state, interpolate between them, and then look at the ground state of this interpolated Hamiltonian, what's going to be the power of this? And in the infinite limit, this question has a well-defined answer, and it turns out that the states split off into a phase of computationally universal states and a phase of computationally useless states. And this is a general result that shows actually that computational power is not just a property of certain special states, such as the cluster state, but is in fact a property of a whole computational phase, in particular, a symmetry-protected topological phase of matter. Now, this might be a bit confusing if this is something that you're encountering for the first time, which is true for no one in this room, because I think SPT is one of the most common terms that has been thrown around in the talk so far. But it might seem, at first that, well, as soon as I go away from the cluster state, I'm introducing a bunch of kind of useless junk in the form of this product term. How could these states be equally as powerful? And that would be a good objection. And indeed, there's a catch. As I go away from the cluster state, as I try to do these rotation operations, I incur logical decoherence. So my rotations are essentially no longer error-free. And it just turns out that if I'm working within the cluster phase, there are techniques I can do to mitigate this decoherence such that these states are still computationally as powerful as the cluster state when taking in these techniques into account. Another objection might be that, neither I nor you nor IBM has an infinitely large quantum computer in their backyard, and any quantum computation takes place in a finite setting. And this notion of phases is really something that only makes sense when you look at infinite systems. Fortunately, there's been new formalisms developed, in particular, connecting the string order parameter from condensed matter physics with computational order here that works just as well for analyzing computational power in finite resource states, which is going to really help if we want to demonstrate anything experimentally. So here I've depicted the simplest test that one can conduct to measure the computational power of a state. So one can prepare in a ring the interpolated ground state of interest and logically input a poly X eigenstate. Then by doing rotations by measurement, one can do a rotation by angle beta and a successive counter rotation by negative beta separated by 2 qubit sites. Finally, one can take the output from this and measure the expectation value of the poly X observable. And if I was working with the cluster state, well, the action of this would be, well, this beta and negative beta will be perfectly canceled. My output is just going to be exactly what I started with. So I should just get 1. So in other words, a perfect computational power state. But as I go away from the cluster state, I should expect that to drop off as my operations in these rotations have more decoherence associated with them. And here, credits to Arnav for producing these theory plots here. We have what this looks like if I perform this experiment in a sort of thermodynamic limit for large system size. We need to see that And the phase diagram splits off into two very distinct areas. On the left, we have the cluster phase where we have computationally useful states that can harbor rotation. And on the right, we can see that essentially the computational usefulness of these states immediately drops off. And these are as useless as the unentangled product state. For finite states, this drop-off is not quite as severe, but one can still see this trend that as I go away from the cluster state, this computational power parameter, it drops off. And kind of maybe the most interesting takeaway to note here is that really computational power is a robust property. Like it doesn't drop off the second I move away from the cluster state, but really I still have states that remain powerful even if I go away from it a little bit. And this gives us a first object of interest, can we reproduce these things? And the second thing that might be of interest to explore that I mentioned earlier is, how is this logical decoherence actually managed? So in the infinite limit, there's a pretty clear picture if one avoids the mathematical sophistication, which I will avoid talking about for now, for how this logical decoherence can be managed. Because the error that is incurred by rotation operations when doing rotations on states away from the cluster state is quadratic in the measurement angle, this then invites a method where if one splits the rotations, then the total error incurred can decrease by the amount in which this rotation ends up being split. In particular, if I have an infinite number of qubits to work with, it'll be beneficial to split these rotations for some distance much larger than the correlation length of the system, so these rotations can all be treated independently. Now, in the finite case, this maybe isn't so clear because now I only have a finite number of qubits to work with. I can't split up my rotation to be arbitrarily small. And now I have this trade-off of, do I split my rotation as much as possible? But these rotations can no longer be treated as independent, and the sum of all these decoherences is going to be greater than just the independent sum of each. Or do I still, kind of try to work in this limit where I can treat the rotations independently? And again, I don't claim this work here to be mine, but this is a question resolved in Arnav's master's thesis, which we'll talk about at length in tomorrow morning's talk. But the optimal strategy turns out to be to split as much as possible, even if one ends up working in a regime where these rotations are no longer independent. So in some sense, a counterintuitive non-textbook regime. So this gives us three things that we could try to address in an experiment, three things that would be interesting to explore. For one, can we reproduce this simplest test of computational power? Those curves of the computational power versus the interpolation parameter, would we be able to reproduce those in an experimental setting? And if that seems to be manageable, could we then move on to demonstrate these techniques for mitigating decoherence in an experimental setting? And that brings us to the actual devices that we would end up doing these experiments on. So as I mentioned in that brief one slide review of MBQC, the circuit model is really the dominant kind of, you see it everywhere, model of quantum computation. And IBM, whose devices we decide to use for this project, are no different. And the first thing to note about IBM's devices is that they don't support universal connectivity. In other words, if I say try to entangle this qubit with this qubit in this 5-qubit device, there's no connection that is going to allow me to immediately do that. So if I want to produce a cluster state, producing this 4-qubit cluster chain is quite easy because I can apply entangling gates in between these neighbors. But now there seems to be the problem of creating the cluster ring appears to be non-trivial. There is the kind of simplest, most brute force approach would be a sequence of swap gates where I switch this qubit over here, apply an entangling gate, and then switch it back. But 2-qubit gates are the most responsible for errors part of the whole computation. And if possible, we'd like to mitigate that. So a slightly more clever solution, which was, I think, briefly mentioned in discussion of the in one of the talks earlier today, that turns out to be local complementation, and where we can use a special property of graph states or cluster states such that we can actually transform between cluster states just by a specific sequence of local unitary operations. So just via local unitary operations, I can start with this cluster chain and end up with a cluster ring, essentially doing some software tricks to simulate a ring, even though the architecture really supports a chain natively. And the second step of trying to reproduce this result experimentally is we actually have to create these ground states that we're interested in doing measurements on. Yes.
Sorry, does that only work for the 4-qubit chain, or does this work for arbitrary chains that via a sequence of local computation technique from open boundary conditions?
Right. I think there's essentially a specific operator that does a certain type of remapping. I think in some sense you get pretty lucky in the 4-qubit case where this is accomplishable. I don't think it's very trivial to generalize this to systems of arbitrary size. And Aslan, who you might enjoy talking to, this is kind of one of the core parts of this project of how do you reduce MBQC computations through local complementation. And I remember he actually had the same question, because he would find that extremely beneficial if a more general sort of identity existed. But I don't think it's quite easily generalizable. So if someone is more knowledgeable on the topic, please do correct me.
There is someone on the dribble on the topic, which is Rafa Hannah. He'll come to the dinner tonight. I think he did computer search for this equivalence of larger chains.
Yeah.
As far as I recall, and I think he did find it. You don't seem surprised.
Yeah.
Maybe you did the same computer search. Maybe you have argumented just when I checked Rio's knowledge. I don't know. What is it?
I don't think so. I mean, at least the intuition that I'm drawing from is looking at a particular Bell inequality, right? But summing up all of the stabilizing elements. And essentially it's known that if you construct one of these Bell inequalities for graph states, if the graph states are local unitary equivalent, then they should get the same value, the same bell down, right? But the bell down is actually different for
Okay. And how is it? And for the 4 chain, this isn't so. For
the 4 chain they're equivalent. Yeah, for the 4 chain they're equivalent. But I think the 5
Okay. Yeah. I might comment though, say there are architectures that IBM has where, say, we want to use a larger ring. They might support that. So there is one device that say has a 12-qubit ring.
Sure.
But for one, that costs money, and for daughter's thesis project, that's not something you want to be burning too much on, quite yet anyway. And also you want to be using, in some sense, the lowest number of qubits possible, because if you're just trying to was shown by Amrit that you go past, say, 10 qubits and you kind of can't see anything. Right.
Yeah, but you can reach.
All right. So now we get to this problem of actually having to find and then construct these ground states on the IBM quantum devices. So again, we're starting with this Hamiltonian. We want to find this ground state, and of course, I know that at least there exists some unitary that can connect this ground state with the cluster state. But just knowing this exists isn't particularly useful because I know nothing about it a priori. So this doesn't really give me a way to implement this. But by pulling out cluster state stabilizers from this cluster state, it turns out that I can exchange the unitarity of this operator to obtain a simpler representation of it that only consists of poly I and poly X observables. So I've reduced the complexity in describing this operator as a first step. Further, at least for small systems, say the 4-qubit ring that we're looking at here, we can make the assumption that T is a local operator. And from this and the translation invariance of a ring, this T operator actually turns out, well, it's parameterized just by 2 parameters. Arguably, I suppose 1 if you just make define A to be 1, but in any case, you've really reduced complexity of this transformation operator, and now you have something that can be found efficiently, say, through a classical optimization algorithm, which Dimitro developed in one of the earlier stages of this project. So this gives us the circuits that we might try to run these experiments with. We would start by creating a cluster for a chain. We then do this local complementation trick to generate a ring. We can then apply this transformation operator to get a ground state of interest before doing this rotation counter-rotation protocol to extract that computational power parameter. However, of course, there's a catch. So in trying to find this T operator, we made this exchange of unitarity. However, of course, all quantum gates that you can implement are going to be unitary. So there's a bit of a tension here. Non-unitary operations, in general, there's not going to be an efficient way that I can implement that. So we do a bit of staring and do our favorite trick of just redrawing a couple brackets. And we make the observation that, well, an expectation value is just a sum weighted by probabilities. And a given probability that I measure J on this interpolated ground state is just the probability that I measure T dagger of J on the cluster state. In other words, what if I don't implement this T operator at all and instead just implement the cluster state and measure it in a rotated basis? And this is going to allow me to get essentially equivalent measurement outcomes while skipping this difficult problem of actually having to implement this T operator. The problem decomposes, I can push it to the measurement and worry about it there. So graphically, this looks something like this, where I've taken out this implementation of T, and now I'm just changing the bases of measurement to obtain equivalent outcomes as if I had implemented this operator. Now, there's one more complication to note, and that's the fact that, well, non-unitary operators aren't going to preserve angles. So if I was originally measuring in an orthonormal basis, as one does with quantum measurements, after applying this T operator, these two may no longer be orthogonal. And I don't have a way of just measuring in this non-orthonormal basis in a single experiment. And the resolution to that is, well, given these two vectors, I can always, of course, define vectors that would be orthogonal to them. And if I then conduct a sequence of experiments, so not just a single run, but a sequence of them where I measure in these, actual orthonormal bases, I can then combine the outcomes of those, post-process the outcomes, and this will give me the results as if I had measured in this non-orthogonal sense here. And here is the result of running this simulation just on my computer. Of course, 4 qubits. You really do not need to do anything fancy. Any modern device can accomplish a 16 element matrix or vector just fine. And what we see here is up to statistical fluctuation. The simulated circuit results perfectly match that of the theory prediction. And this really is just showing that the algorithm we constructed is correct. Then we get into the more interesting part where, okay, well, what happens when we actually run this on a real quantum device? And here we see that there is an overall drop in the fidelity of the values due to various sources of experimental noise, but the overall structure of the curve really has been retained in the experiment. And really what this demonstrates is a experimental verification of this property of the robustness of quantum computational power. I can go away a bit from the cluster state, but I still retain computational usefulness, I don't have to just work with the cluster state. Yes. It is worth noting that their measurement error has mitigation has been applied here, but no gate error mitigation as of yet. Yes. Good point. Thank you. And now we get into kind of the second chapter of the experimental part of this talk, and this is the making the experiment more quantum mechanical. And now we'll finally get into whatever that means. So in our current setup, we found the coefficients for this T operator classically, and we've done this kind of clever post-processing algorithm trick to also apply it classically, post-process the results, and obtain them as if we had conducted the measurements that we had wanted to. But one could first object that there appears to be a lot of classical searching done here, and if we're trying to do a quantum mechanical demonstration, maybe this is a bit more classical than you would like. Another objection might be that this isn't fairly generalizable in the sense that this classical search for this T operator becomes intractable when one looks at a larger systems. So it becomes of interest, can we actually find this transformation operator on a quantum computer? And a very natural method that would allow us to do so is going to be a variational quantum eigensolver algorithm, where we can conjecture some ansatz T prime, parameterized by a VQE parameter theta, measure the energy with respect to the Hamiltonian of interest, and by minimizing this and finding the value of theta that minimizes this energy, we can find the value of theta for which we can, I guess, have an equality here, but in general, well approximate the transformation we're looking to find. To be more specific, if the target form of theta that we're trying to find is this local operator consisting of i's and x's, a natural ansatz to make then is to say, let's parameterize our T prime by this cosine theta of I, sine theta of x, and minimize this per site energy of the Hamiltonian, where you have the stabilizer expectation and the local magnetic field expectation weighted by cosine alpha and sine alpha. Of course, I give the ansatz, this local ansatz here, but the technique in general could be generalized if we wanted to look at larger systems. As kind of I noted before, this local form of T doesn't work when one starts to look at rings, say larger than size 6. So if we wanted to try to probe ground states for larger systems, we could start to add more sophisticated terms to our ansatz that were non-local, say. Yes.
Any reason why it does not basis, like just identity that?
As in, so why are these real?
Yeah.
Okay. The reason isn't immediately coming to mind, although I think I have either thought about this or heard what the reason was before, but I can get back to you.
Yeah, I do remember the numerical results that it turned out this way. I also remember that we discussed the reason and understood it.
Yeah. Robert, do you by any chance remember why these two coefficients can be assumed to be real?
Well, another complete answer, but I mean, I can maybe add that also the division theory says so. I mean,
right.
You can,
I think that's satisfying. All right.
I think that was the reason.
Right. And yeah, I mean, and in perturbation theory can also be used to motivate this local ansatz as well. It might be worth pointing out where this is the essentially lowest order contribution that one gets. So now we get into actually, carrying out this VQE, and it essentially comes down to measuring these two expectation values, this cluster state expectation value and this local magnetic field expectation value. So how might we do that? So here is kind of the first algorithm one might think of when trying to perform this operation, where one first prepares the cluster state, in this case, the cluster ring. Then there's this probabilistic implementation of this T prime operator parameterized by theta. Why probabilistic? Why this kind of interesting looking ancilla construction? This comes from the fact that, again, this T prime is not unitary. So we can't just, put it as a gate here. Instead, we have a probabilistic implementation that will implement the correct form of T prime if this measurement outcome gives the correct value. And having prepared that ground state of interest, one can then measure, say, either X or ZXZ, at whatever location in the ring one wants, because it should be the same everywhere. And after averaging the experiment multiple times, one could obtain these expectation values as a function of this VQE parameter theta. Now, of course, this doesn't look too promising. One thing might be to say that it requires 8 qubits to do what should be a 4-qubit state. Another thing is that if I measure the wrong outcome, I'm now no longer preparing the state of interest. So there appears to be 2 roadblocks here that would make this extremely inefficient. However, it turns out that this fairly large and inefficient circuit, and shown here for the case of the local magnetic field measurement, reduces to the repeated running of just a single qubit circuit and then the post-processing and batching of the outcomes. So how does this seemingly, relatively gigantic circuit reduce to this very simple form? While I won't go through the full derivation, I can give 2 of the ideas that go into this simplification. The first is going to address this issue of measurement, erroneous outcomes on the ancilla qubits. So it might seem that, say if I have these 2 erroneous outcomes here, I've now prepared the wrong state and this entire experiment shot has to be thrown out. But one trick I can play is I'm always free to pull out a cluster state stabilizer from this cluster state. And when these Zs move across these C0 gates, these outcomes actually become corrected and we can now suddenly prepare the correct state. So we don't have a state preparation that has a very low chance of succeeding. In fact, if we have any even number of errors on the odd and even sublattices of our ring, this is correctable through a specific sequence of pulling out stabilizers. And really what the gain here is that even if I were to say look at rings larger than size 4, the error probability is not going to exponentially increase as I add more ancilla qubits, but it's actually going to be constant due to the fact that all I require is that there's an even number of errors. The second trick really is more of a sequence of circuit identities, but here I've presented the unit cell of the VQE circuit. So the first observation is I can move this X measurement past the C0 gate. It introduces a ZS gate condition, depending on the outcome of what that measurement was. But this disentangles the ancilla qubit completely. And further, I can say, well, what's left in this residual circuit is just a half teleportation that we see in, say, the construction of measurement-based quantum computing. And now, through these 2 simple observations, I've disentangled the qubit and also removed one completely. And through repeated application of this, I can condense my originally fairly large circuit to a very simple form. And I didn't show the case for the cluster state measurement here, but it turns out that basically for any ring size, one can condense a VQE circuit of size 2n to either just a circuit of size 1 or size 4. And there's this kind of intriguing result here where preparing this interpolated ground state is inefficient, but getting these measurement outcomes really is not. You can use quite simple circuits to obtain those measurement outcomes, perhaps hinting at some deeper compilation type structure that still might be yet to be explored. So what are the results of actually running these circuits? So these are the results for the local magnetic field and stabilizers when I've executed the simplified circuits for the VQE. And noting this periodic structure, one kind of immediate intuition to get rid of the occasional jumps due to the experimental error comes in the form of trying to fit a Fourier series, or, well, not a series, but a finite Fourier sum. In doing so, one can see that the predicted values for these curves and the fit values really match up quite well. And then if one tries to calculate the coefficients of the transformation operator using now those fit values for the expectation values, we can observe that, I have this really good agreement with the classically obtained value for this transformation operator, or at least until I approach the product state where I have this fairly sudden anomalous behavior. And this in particular can be explained by the structure of this magnetic field curve, where there's this definite leveling out as one approaches theta equals pi over 4, leading to a plateau and eventual jump as one tries to calculate, minimize and calculate these coefficients. So having obtained this transformation operator quantum mechanically, the final step is to redo those experiments that we originally did with the classically obtained transformation. And we see that, again, up to this now new phenomenon of the failure near this product state point, we see the curve from the theoretical prediction and the curve from the experimental result matching up to this decrease in fidelity from experimental error. So that was a lot of plots. So it seems about high time to wrap up and put a bow on the presentation. So the next steps is going to be to move to a larger system size where we can not only observe how this computational power changes with this interpolation parameter, but also observe techniques for mitigating the decoherence. And, tying everything together, why is this all interesting? This is really the first experimental demonstration of the robustness of quantum computational power. And, I pitched two initial questions at the start of the talk. One was that we want to understand quantum computational advantage. Another is that we want to do cool things with these noisy and intermediate scale quantum devices. And our results nicely fall in the middle. Thank you very much for listening, and I'll be happy to take questions.
Dumb question, but you were saying how you're measuring that T and then it's only up to a particular duration.
Yes.
Would that be contributing to part of that deviation?
Right. So this drop could potentially be explained by the fact that we've simplified the form of T. Is that the question? So that is a very good theory. I think what it is, or at least what I observe, is that this is a combination of the plateauing issue and very slight deviations from the theoretical curves for xi and ki. So if one tried to compute these coefficients just by using expectation values that you can just quantum mechanically calculate, you do find agreement. So it's more of a kind of a combination of two unfortunate things. One is this very slowly varying plateau effect, and another is the fact that even if one does this Fourier fitting, you still get some deviations due to experimental noise. And in trying to calculate the coefficients, that effect is most obviously seen where it's varying the most slowly. Yes. Yeah.
Space condition is typical exponent is the Ising phase condition.
good question, but I don't think I have the background to answer, unfortunately. But
Save it for tomorrow.
yeah,
On
yeah. In many ways, I think this
Yeah,
talk
yeah.
was the cart before the horse, where I'm presenting on demonstrating theory results, which will then be discussed tomorrow morning.
Talking about this phase transition, the results that you were showing were 4 qubits, right? This
Yes.
curve like that. And the last points you were describing them as, or the reasoning was that they were from the product state.
Mhm.
In this so small finite system, it seems from your curve that you are actually not describing this transition, indeed, that you are mainly in the cluster phase. Did I understand correctly?
Right. Yeah, I think it would be correct to say that, for one, in general, the language of phases can't really accurately describe what happens in this finite regime. Indeed, I think in the finite case, it's true that the gap never closes as one varies this interpolation parameter. So in some sense, it's not as meaningful as a way to describe it, which is why this notion of string order parameters, which works well in the finite case, is a more useful characterization of computational power. I don't think I completely answered your question, but I think you are right in saying that there isn't really a well-defined phase transition. There's kind of no distinction particularly there at all. I think.
Okay, something in between the question and comment. Regarding the previously asked question about difference between theory results and MBQ. If one looks at the curves of computational power decreases, right? Keep this topic.
Okay.
And you have a deviation between theory and experiment. I suppose that for 4 qubits, the theoretical result is pretty exact, like something like exact diagonalization.
Yeah.
For the ground state. And there one could wonder indeed whether the ansatz for the T operator contributes to the error between the theoretical and the experimental result. Right?
Yes.
But in this plot, which you show here right now, you compare the, as far as I understand, the classical optimization of T in this ansatz with the T optimization within this ansatz.
That's
so
right.
This
yes.
jump cannot come from the form of the ansatz because
That's
then
right.
it would appear also in the classical.
Right.
kinds.
Yes, that's a good point.
I have a comment. So this ansatz for 4 and 6 qubit is exact. Stops being exact at 8, and it's actually connected to this so you kind of need a lot of qubits to say this, like the coherence measurement that has something to do with the length scale, right? That's the coherence measurement. The management works, but for 4 and 6, there's not enough qubits to show it, but there's also like no length scale appearing. So this ansatz that Rio is using, it doesn't really have a length scale. It's like a local operator on top of a cluster state.
I have a question which is related to what Corina just commented. So in the theory curves in power course, did you use the variational ground state or use the exact ground state of the
Right. Okay, so here, this is the variational ground state, but here it does coincide with the exact one, as Dimitra noted, for 4 qubits. And for the earlier plots of the computational power versus the interpolation, I believe that was done in DMRG. Arnav used DMRG calculus, right?
Yeah, then I think that's it's pretty amazing that for the non-quantum computer simulation result, the theory curve and the simulation curve somehow exactly match.
Right. Yeah, I mean, in some sense, right? I see.
Yeah, I mean, that just means to say that the critical variable was.
Right. Yeah. Yeah.
There was a part where you talked about how the basis wasn't necessarily a formula, or you have to kind of average over a bunch of different kind of things.
Yes.
I don't completely understand how that could work, but my question is, could you also use some kind of variation scheme to find some TML of such that it's not, or is like that TML predetermined?
Right. So it might be possible to say, look for a form of, or this original U is a unitary operator, right? Like I can find a unitary operator that connects these, and it might be a valid question to say, oh, well, can we just try to look for that unitary U directly instead of sacrificing this unitarity, looking for something that's going to bring in all this non-orthogonality. But I guess one thing that perhaps might make that difficult is when doing a variational algorithm, one needs to have some ansatz to start with that one optimizes, and it's kind of a pretty slippery place to start with a unitary operator one knows nothing about. So I would say it'd be possible to look for one that didn't sacrifice the unitarity, but that might also give you less to work with and in actually trying to find what it would be.
Maybe just for clarification, could you repeat, please, how your disyntactic trick works?
Is this for the VQE?
Yes,
Yeah.
I think I have this argument.
Right. So initially, we appear to have this ancilla kind of entangled to the rest of the circuit, but we can observe that, okay, well, the next measurement and this C naught should commute. So I'm free to push those past each other. I do obtain this phase kickback here. And further, one can do the half teleportation. And really, I've removed a qubit, and I can just reduce this finding of the outcome to just now a classical coin flip if I removed it in the half teleportation. So yeah, I've removed a qubit, and Dancel is completely disconnected from the rest of the circuit.
Can you actually imagine what kind of VG you would need to use in order for it not to be classically suitable? Like, I mean, just dream a little bit if you have like many qubits.
Right.
Of course, not for 4 qubits.
I mean, certainly one would need to have non-local terms in this transformation operator, like
Large steps.
Yeah, right. That would also. Yeah, that's sense. It's just optimizing over done forever. So very tough. Shall we?
Yes, thank you.